All right.
Oh, of course they're gonna battle me. Okay. And we should be live, but
All
there's no
right.
guarantees. Of course,
Hmm.
we require external observers to confirm our existence. So
That's right. Or deny it.
or
That's
or
yeah.
deny to, yeah, exactly. If someone wants, they can deny our existence, and that will throw the whole theory of we exist into doubt. There we go. I see a couple of people saying that we exist.
All right.
How's
Let's
it
see.
going?
Great. Yeah, I've been anxious to talk to you for about 15 years now. So it
That's
only took a
amazing.
decade and a half.
I had no idea. Now we covered every well, the minutia of your work, but I had no idea that you were watching it happen unfold in real time. But I'm sure we'll get to
Oh
all of
yeah.
that. I today I'm interviewing Dr. Brian Keating, author of Losing the Nobel Prize, and so there's your context, everybody. Uh, so Brian, who are you? What do you do?
I ask myself that frequently,
I
but
know.
I am an astrophysicist. So I am a director of a large telescope project. I am the professor of physics, and I am also sort of a lifelong astronomy amateur astronomer nerd. And I've lately become bitten by the writing bug, by authorship of this book, my first book, and possibly my only book. But
Yeah, yeah. Writing a second book is the big question, right? After you write the first one, it's like whether or not you ever want to do the second one.
right, all these snobs say, "Well, you wrote a book, so you're a writer, but are you an author?" And
Yeah.
I don't
I don't know what
know.
that
Does this
means.
answer your question?
Yeah.
Shut up.
Yeah, stop
Yeah.
asking. Come on. Anyone who's written a book knows that writing a second book is not to be taken lightly.
No, and people are, and I do feel very lucky that people are approaching me to write another book, which I don't think would happen if they really hated my book or
Yeah.
it wasn't popularly received. And as a recovering academician and still involved in academia as you are, you might get 10 papers, 10 citations to a given academic research paper. But, a book like this, sold 12,000 copies, around the world. And that means, people on every continent that at this very moment, there is a man in Antarctica who has a copy of my book.
Yeah.
That one was free, so I didn't get any
Right.
royalties
Yeah, but the
off that
fact
one.
that your
But
book made it to Antarctica is pretty amazing.
it
All right.
is.
All right. So, I mean, you've got a fascinating story, and I want to get into it, and I want to sort of talk about the future as well. So, I'm, and we have a very technical audience. They're going to understand a lot of this stuff. So, let's sort of go back a bit and just talk a bit about the your work as an experimenter and an instrument designer and leading up to your objective for searching for primordial gravitational waves.
Yeah, so it's a very astonishingly interconnected story as it turns out. I'd always been interested in astronomy since I was a kid, and soon after that, I became even interested in winning a Nobel Prize for reasons I describe in the book that trace themselves to really wanting to get approval, wanting to get sort of recognition, and all sorts of reasons that people strive for any sort of accolade in science and outside of science. How many Oscars and Academy Award type things are there in the world? But for scientists, winning the Nobel Prize is really the paramount ultimate achievement beyond which you really can't aspire to. And for those of us in academia, yourself, your listeners included, watchers included, once you are successful as a scientist, yeah, you're used to, and maybe you welcome getting graded, getting appraised, and so forth. But as you know, once you go to graduate school, I mean, I haven't gotten a grade in anything, luckily, in 2 decades. And so, how do you fulfill that grade grubbing tendency that many of us have? Well, a lot of us, it's winning accolades or getting, winning the Coliseum like gladiatorial battle that it takes to get a faculty position. And then once you get that faculty position, moving up to the tenure track and getting promoted. So I didn't think it was a realistic possibility that I'd ever win the Nobel Prize, but that was sort of my goal, to do something worthy of a Nobel Prize that was concomitantly something that had never been done before in the history of the universe, and that was to reveal the properties of the Big Bang itself. And what we're fascinated in cosmology today is the question, which is more or less an eternal question, is whether or not the universe itself is eternal. Is it cyclical? I mean, most scientists and non-scientists are now aware of the Big Bang and believe in the Big Bang, whatever that means. But in reality, there's no such thing as really the Big Bang theory currently in cosmology, and the controversy surrounding that makes up a good chunk of what I wanted to describe, and the excitement of getting paid to do experimentation to determine what happened at the very earliest moments.
Right. I mean, the Big Bang really covers the fact that the universe is expanding all around us, and that if you that everything is getting less dense over time, and if you run the clock backwards to the beginning, it says that things must have been more dense in the past. But what happened before that is the job of some other theory.
Exactly
I
right.
don't
So
think
it's no
it's
more, an origin of species as than existed before the origin of species. In other words, physicists, scientists in general, are universally obsessed with differential equations, and as you know, every differential equation requires what's called boundary conditions. How does your physical system that you're modeling, be it predator prey, or be it thermodynamical systems, how does it interact with the environment that contains it? And the other factor that must enter into all calculations in physics are the initial conditions that describe what happened in the beginning. Well, as I say in the book, the Big Bang, if it is the true origin of time itself, is a unique moment not ever witnessed, since, and certainly, nothing like any moment because that we've experienced, because there was no priority. There's nothing that came before it.
right.
The universe started without being in the middle of the story. It is the story, and yet, as I say, most cosmologists right now, they might take for granted that the Big Bang is expanding hot acceleration from the early universe, and the universe been cooling, expanding, accelerating its expansion even over the past 15 13 billion years. But we lack a real in-depth understanding of the exact moments and the conditions that took place, if you will, at the origin of the universe itself.
And it's a really tough time to probe because you've got the cosmic microwave background that obscures our view beyond the first 340,000 years after the Big Bang. So it's a very difficult time. You can't use the regular technique, light, and so you have to use some other technique, in this case, potentially gravity.
Right. Yeah, exactly. So I'm sitting here in UCSD in my office, and the office behind me there is occupied by one of our executive vice chancellors here. She's really the woman in command of the entire university. Don't tell the chancellor that, but it's basically true. And
It's
if
okay.
I want
Nobody's
to,
watching this. It's not recorded.
yeah, and if and if I wanted to, I couldn't even spy on her through this wall. It's pretty opaque, isn't it? But if I could put my ear against the wall using a different form of technology, using a different form of radiation, if you will, sound radiation, I could determine what she's talking about and how she's planning to cut my pay and so
Mm-hmm.
forth. But in reality, the eyes are not the only form of sensory organs that we can use, and essentially we don't use telescopes, look through them the way Galileo used to do and so forth. But we are able to use other forms of radiation. And what was so cute to me when I came up with the idea to test whether or not we could experimentally probe the first moments of the quantum gravitational epoch of the inflationary universe that spawned the rest of the story that we're now a part of, the Big Bang itself. I was tickled by the fact that we're actually using the cosmic microwave background, the CMB, the famous 3 Kelvin backgrounds discovered by accident by Penzias and Wilson 54 years ago. That we would use that as our detector. So we would use photons as a sort of film, and on this film would be exposed waves of gravity from an earlier epoch. So the CMB, the 3 Kelvin background, was produced 400,000 years after the Big Bang, and that's the end of the line. When it comes to photons and electromagnetic radiation, as you said, you can no more see past that, see through it, than you can look through a mirror with your eyes.
Right.
But you can use waves of gravity to see earlier and further back in time, and that's exactly what we thought we did with the BICEP 2 experiment.
Right, and the goal to look back with that inflationary period, of course, is that there are a bunch of problems with the Big Bang, or there are a bunch of issues that the Big Bang questions the Big Bang brings up about how parts of the universe seem to be the same, even though they should be they're on opposite sides of the sky and they shouldn't be connected in any way, and that there's a bunch of other issues. And so, of course, this idea of inflation to describe this really rapid expansion early on to get around that, and yet inflation has been a really tricky thing to try and find any observational evidence of, especially because, as I mentioned, the cosmic microwave background is obscuring our view to this, and so to find clues is tricky work. So I love that idea that you're using the CMB as a film to expose this earlier epoch onto. So you went about designing an experiment to be able to actually do this.
Yeah. Yeah. The experiment had to be of a unique characteristic in some ways and highly advanced in a certain sense. But it's also, the simplest of all possible telescopes is that it's a refracting telescope. So, the telescope behind you is presumably a refracting telescope. And even the gigantic, Keck telescopes and the Hubble telescope, at some level, they have refractive optics in them, namely lenses and corrector plates and things like that. And I thought, well, at a basic standpoint, all telescopes have these refractive elements. What if they only had refractive elements? What if you got rid of these mirrors, which can, in some ways, introduce what are called artifacts, systematic effects that obscure and bias the results that you're looking for? These are instrumental effects. So you could build the cleanest, most simple telescope, and lo and behold, it turned out to be a refracting telescope with two lenses, exactly like the one that Galileo used in 1609, to really overthrow our
I
view.
think I
Our
have
view
one behind me.
Yeah, that's right. That's you in the background, right? You're
Yeah.
looking up at Pluto. And for us, the simplicity is beauty and simplicity is elegance. And that leads to a cleaner, more vibrant experiment. And for seeking signals such as we did, we were looking for signals that are about 1 part in a billion of the background of even the frigid location where we put this telescope. We would have liked to put it in space to get rid of all atmospheric contamination, but we didn't have the cash to do that, and NASA wasn't willing to do that at the time. They're only now really investigating the possibility of building a space telescope to do the kind of science that we started doing back in 2001 with BICEP, which is a refracting telescope we put at the bottom of the planet at the South Pole, Antarctica.
But I love this idea of building an instrument specifically to answer a question that may be at the very limits of what is possible to discover, but it's done on a relative shoestring than the billions it might cost for a space-based version. Well,
Yeah,
I'm sure you've got a more accurate budget.
yeah,
And even knowing if you're in the right ballpark, if you can sense a whiff that there's something there, then you can come back and follow up with more detailed observations. And I think it's a real winning strategy. I see this same approach happen again and again, where people are, they're building just enough telescope and no more to
yes.
to probe this situation, and then if you get a positive result, then you can follow up with something that's more specific and beefier, and you've learned all your lessons. I mean, even like what's been happening with LIGO, right? Like the first detector, the first time they built this thing, they weren't even sure they would ever be able to detect anything. But a lot of people thought it was crazy, and
Right.
they didn't detect anything for the longest time. And then they came back around with an update to it. They did make a couple of detections, and now we are just a week into its new run, where it's like 40% more effective than it was. So I think,
Yeah.
I admire that experimenter's mindset about, like, I mean, in business, you sort of have this concept of the minimum
Minimum
viable
viable.
product, right?
Yes,
And it's
exactly.
and
Yeah.
it's that, what's the minimum viable instrument to.
Yeah, I've been speaking. Somehow I get connected to these really interesting entrepreneurs that do podcasting too, like Dave Asprey, who runs this Bulletproof radio podcast. And we were talking just a couple weeks ago about how, all scientific experiments of this caliber are basically startups. I mean, I have a payroll, I have employees, I have travel, I have receivables. I don't make money on any sale. In fact, I lose a lot of money in that sense. But my currency is citations, is influence, is how we, and this hasn't changed in hundreds of years. Going back to Galileo in my research for the book, I really realized that Galileo was he was an entrepreneur and he wanted to maintain a monopoly that he had on his telescope, which wasn't his invention, but his improvements were so substantive that you could really call it almost a unique device that he had created because it had so much more magnification power but and freedom from artifacts, these systematic effects. He did all sorts of amazing things in retrospect that allowed him to see things like the phases of Venus, the moons of Jupiter, and of course craters and mountains on the moon. And he was smart, he was shrewd, and he had no small amount of motivation because he had a bunch of illegitimate children and mistresses, to support
Yeah.
over there in Florence, because he had had dallied a lot in his earlier youth. And if he had given up everybody, had told everybody the secret to how his telescopes work so effectively, he would have lost his monopoly. But what he realized is he could publish a paper, self-publish a book called The Starry Messenger, Sidereus Nuncius, and that book would be the instruction manual for a product that he would never release into the public, even to Kepler. He never really shared the product with Kepler for fear of being scooped. And that type of competitive nature that most people associate with business is actually rife throughout all of science. And it is a very interesting thing to consider how similar science is to entrepreneurship. And I always joke, it shouldn't surprise people because the Big Bang was the very first startup there ever was, right?
Yeah. And so, of course, you built this instrument, you gathered up your data, and I think a lot of people remember we talked about it a lot,
Yeah.
about the announcement that you guys made.
Hmm.
So, can you sort of talk a bit about how that went down?
Yeah, it was exactly 4 years ago this March. It
Wow.
was
Okay.
St. Patrick's Day. Yeah, time really flies when you're studying billions of year old things. And we made an announcement at Harvard University that the successor to the project I invented called BICEP, imaginatively titled BICEP 2, had made a discovery of these waves of gravity percolating and permeating the early universe space time fabric. And that was causing this particular type of polarization pattern, which we refer to as B modes for a very technical reason. But really, these correspond to if you were to make a map with your polarized sunglasses and twist the polarized sunglasses around on every point in the sky, you would see a swirling pattern of polarization vectors where the light was preferentially dominating in this swirling configuration. That was where these waves of gravity and the primordial moments of creation, perhaps, were the strongest. And that was as close to direct evidence of, say, the quantum gravitational epoch to the inflationary epoch. You were detecting the shrapnel of inflation. And this is the goal that I had when I started the project that was the predecessor, Bicep One. And by the time we had made the announcement, it was 3 years after taking data with the second generation instrument called Bicep 2. And so we had two sets of experiments that had basically seen very similar evidence, although one was much more sensitive than the other one. And we decided we would go ahead with this because this is literally the greatest quarry in cosmology, is
Yeah.
understanding how the universe began.
Yeah. I mean, and your book is called "Losing the Nobel Prize,"
Yeah, spoiler
and
alert.
and I think that is absolutely, you know, I I mean, someone would have gotten a Nobel Prize,
Yeah. That
and
day, I mean, about seven people, including, former Nobel Prize winners, were speculating on which one of us would win the Nobel
yeah,
Prize. So
yeah,
people say, well, I don't see how you can lose the Nobel Prize if you didn't win it. I'm like, well, yeah, I guess you can't lose an Oscar, right? You
yeah,
can't, you,
yeah.
it's kind of ridiculous.
But let's talk about how it all sort of went a little wrong, and
Yeah.
that moment where the Planck team were gathering up their data and they were mapping out all of the dust.
Yes. The
Mapping out the
film.
dust in the across the skies, and how the dust was the cause of the
Yeah, so
downfall.
we it's interesting because recently people have been talking about other sorts of big announcements that are coming up. We're like 2 days away from
2
this
days
event
away. Yeah,
horizon,
yeah, yeah.
right?
Yeah, the
Everyone's on
chat
social media.
really wants us to get into that, which I hope we'll have some time to
Yeah,
talk
maybe
about
we'll
that.
have some chance to talk about that. So yeah, part of the discovery relies on the South Pole as well. So the experiment was known to have, basically two different types of potential artifacts that can contaminate the results. One was from the inevitable randomness arrival of heat from other sources other than the cosmic microwave background that we are using as this film to expose waves of gravity onto. And that could produce an excess amount of noise that would obscure a true signal if it existed, and we would be blind to that signal. There's another type of signal which is possibly present from the instrument itself, from the South Pole. Even though it's very cold, it's still hundreds of Kelvin warmer than the signals that we're looking for. And remember, these are about nanokelvin, parts per billion of the already feeble microwave background 3 Kelvin signal itself. And then there are, of course, other signals that are true astrophysical signals, honest to goodness signals produced not by, gremlins or ET or by radio transmitting towers, but actually produced by cosmic phenomena. And in the case of the pursuit of the cosmic microwave background radiation, this had actually never been a problem before. Our experiments had been measuring signals since the 1960s. And in fact, in the early part of the 1960s, when Penzias and Wilson were trying to attempt to communicate with radio satellites in space for the first time, they didn't, of course, want to detect the CMB. They didn't know about it.
Yeah.
They were actually first trying to calibrate their system by looking at the galaxy and trying to see galactic signals, and they couldn't see them. And that made people maybe lulled us into a false sense of security. And for the next 5 years almost, 50 years, people were basically, confident that we could model the expected contamination of the Milky Way galaxy and remove it with enough fidelity to leave behind just the pristine cosmic signals. And this was the case for experiments like WMAP and Planck. I mean, they went to great efforts to remove it, but it was a tractable problem. However, with the cosmic microwave background's B-mode polarization, the twisting, curling fingerprints of the inflationary epoch, the signals that we imputed to be coming potentially from dust, which is the number one contaminant that we were worried about, we modeled them as being much smaller than we should be concerned about. And so, but we weren't really all that settled about it, even up until nearly publication date. And so what we did is we reached out we knew that, this billion-euro satellite called Planck was trying to make this measurement just as sure as we were trying to make this measurement, because amongst other things, they would win a Nobel Prize, presumably. Yeah. And so we didn't want to be gun shy about this. They invest €1 billion. They want to get something out of it, just like LIGO, et cetera. I mean, part of the motivation is you have to pay your bills, and that funding agencies use the Nobel Prize as a proxy for impact. And anyway, so we had pursued, and some of the members of our team, my friends on the team, were members of the Planck collaboration. And so I felt, well, maybe they can just peek at the data. I'd probably take a look at the data, if I were them. But
it
turned out that they turned out that they didn't. And in that sense, I salute their integrity, because I don't know if I could have resisted the temptation to know that we had a signal in the bag. And so we made formal requests. And the Planck team denied our request. Yeah. So it was natural to think, well, they had the sensitivity. They said they had the sensitivity to more than scoop us. And they had the data not just from the small patch we could see from the South Pole. They had it from the entire sky at 9 frequencies, and we only had 1 frequency. And you need multiple colors or frequencies to resolve and tease out the different cosmic contaminants. And so we went to publication with a model that was based in part upon a slide that we had digitized from an more or less informal talk that was on the Planck website, still there. I cite it in my book. And this paper, the slide that was presented in Europe, gave us the last bit of confidence that we needed to go forward with the self-published, not peer-reviewed result and press conference that became seen on CNN and the New York Times and 3 million people on YouTube. And this I realized in retrospect is just yet another example of confirmation bias, which is maybe something important that most listeners might not really be might be surprised to learn about in science.
Yeah, I mean, the question is just to figure out what your biases are. We all have them. The trick is to realize or to start to question your own assumptions, right, to sort out which is your confirmation biases. So I just want to talk about the book a little bit. I really enjoyed the book.
Thanks.
I loved it because I knew how this story ended. As you brought up dust, I saw how dust had been this influence, had been this confounding effort, this confounding factor through so much scientific discovery. It had been the thing that had raised its head time and time again, and that it was clearly your kryptonite. And you and to the point that you knew going into this final decision to actually announce your discovery, I'm sure this was your greatest fear,
that
it would end up being the dust. You knew it could be dust,
yep,
but you knew that Planck could announce before you and scoop the Nobel Prize. So you made the call.
Yeah, and actually, it was a natural thing to really, assume. And what's interesting to me to point out is that we didn't make a blunder. We didn't leave the lens cap on, or we didn't like overlook. We actually spent most of our angst and our neuroses focusing on, what Feynman would say, that you have to assume you're the biggest fool of all, and not be, subject to confirmation bias. But for us, we did go out and we used maybe too much confidence that we had in the lack of attribution to dust. And it was sort of surprising because, as I recount in the book, I originally thought, well, maybe a good title for the book would be A Brief History of Dust. Kind of.
That wouldn't be as compelling a
Yeah,
topic.
I think my publisher, wouldn't be as
Yeah.
happy with that. But it's really true. You look at the book, and you got the book there, and I've got it here. And what's always on the cover of a book? A book jacket. And I used to hate I still hate book jackets, to be honest with you. They fall off, they get dirty, they get torn. But I realized, what's another name? The dust jacket actually serves a useful purpose. It's keep dust off. Like, try putting a wormhole cover on the cover of your book. Like, it's
Yeah.
not going to happen. And
They just
so,
suck up dust. Yeah.
yeah,
Yeah.
but really, dust is ubiquitous, and we were not by any means the first astronomers to really kind of fall prey to the combination of dust and desire, to really understand the universe amidst the dusty environment that we find ourselves located within. And people say, well, how are you going to get rid of it in the future with your next experiment? And I'm always joking. I always show like a giant slide of a giant dust buster, hanging out in the space and sucking up the dust. But you can't do that, and that's part of the challenge of being an astronomer. Is we can't do an experiment. We can't actually say, well, what would the signal look like if there was no dust in the universe versus there is dust in the universe? Or what would the temperature, what would life be like on this planet if the temperature of its star was this? We can't do experiments like our biology friends can do. And yet dust is really mercurial in some ways, because without it, we wouldn't be here. I mean, we have star stuff flowing through our veins, right? As Carl Sagan used to say, it's the iron in our blood, came from the same supernova that made the damn dust that obscured our Nobel Prize.
So I mean, so half of the book is you explaining in sort of gruesome detail and a fairly humble approach at the conclusion, talking about I think there were enough details about how it actually went down blow for blow, and I don't know sort of how much of that you had put in the book and it had gotten cut out or whatever, because it actually felt like you had gone into more detail, and maybe some of it was a little simplified. But I wanted to see all the nitty gritty details. But, and then you break that up with some recommendations for ways that you think maybe the Nobel Prize could be improved. And I think, a lot of your recommendations have been made by many people before. Do you think that you got a little Nobel crazy?
Oh, definitely before the Nobel Prize, before this effort, and before kind of the episode that led up to this. As I said, I had this kind of ulterior motive in my mind to want to to kind of reach out just on a personal side. That I had been driven for a long time to want to make a name for myself as a scientist, to in some ways compete with my father, who was a great mathematician, great physicist, and who had achieved much more notoriety than I had as a young postdoc. And so I want to do something big and unshakable. And I realized that in the writing of the book, that it had become sort of an idolatry, an idolatrous quest for me. And it really remains so for other people. Like, I was reading another book last night. It's called The Telescope in the Ice by Mark Bowen. It's about the ice cube
Yep.
experiment.
Yep.
And the guy on every other page, then the word Nobel Prize comes up. And then I read books by Lawrence Krauss, that came out just a couple months before my book. Nobel Prize on every, as a way of certifying, as a way of a jury, as declaring as sealed science as possible, that the Nobel Prize is able to confer on science. And I realized how the Nobel Prize distorted my vision of what science really should be. And people say, "Oh, you're just jealous. You have sour grapes." I don't think anyone. Someone was asking me the other day, in a different podcast. It was in the context of like LGBTQ, and he asked me, does it feel like you're coming out of the closet to say this? And I said, I don't know, but for me, it was a feeling of liberation to not be beholden to this 3-inch golden, literally
Mm-hmm.
golden idol that you bow down to, engraven with the image of the patron saint of Alfred Nobel on its side. And I realized that it's basically deep within the heart of scientists as well to have this thing exist. So there were very many powerful people that told me not to write this book. It would be dangerous. People love the Nobel Prize. It's an industry. And it's, Sweden's most popular, most important holiday, essentially. They celebrate it on the date of
Nobel
Alfred
Day, yeah.
Nobel's death. Yeah. It's $1 billion industry. So they don't want to compromise. And I actually engaged with the Secretary General of one of the Nobel committees. For the first time in public, they've really taken. So many people have made a lot of the recommendations that I've made. A couple of them are more controversial than others. But to my knowledge, no one from the Nobel Committee has acknowledged that the Nobel Prize really is subject to these very vast biases and problems. And so my contention is I wrote this book. I came not to slay the Nobel Prize, but to reform it. So the title is a play on words in part. Not only did I lose the Nobel Prize, it lost its meaning to me, and also some parts of it need to be lost for the betterment of science.
Yeah, it's a great title. And I think that and I like the recommendations. And I mean, there are other prizes that I think meet some of those requirements that do actually a better job, but they're just not as
No,
popular.
they're not as
There's a
popular, right? I
first
mean,
mover
you notice.
advantage, right?
Yeah,
There's
absolutely. Yep.
yeah.
And nothing like this guarantees that the Nobel Prize will remain. I mean, the Pulitzer Prize used to be much more popular and prestigious than it is now, and it was more popular and prestigious than the Nobel Prize. I mean, the Nobel Prize was supposed to be given out annually to people that made inventions, and now it's become this huge spectacle. And as I said, $1 billion industry, and so I think it has an obligation, just like Hollywood. The Oscars used to be a tiny little affair, and now it's this global thing where
Yeah.
you make and break careers. And I don't think most of my colleagues, I should say, Fraser, I don't think most of my friends down the hall here, I don't think they're thinking about fantasizing about winning the Nobel Prize, in part because they may be doing something real science, which is mostly incremental. It's not this breakthrough once in a century. At the day of the event, Lawrence Krauss said it had advanced human knowledge more than any other discovery, in all of human history. So it's not every day that you're a part of those kinds of experiments. So had we been confirmed, I think that would have held up. And whether or not I won is sort of immaterial. It's like I do feel like these criticisms are valid. And I should say, only about 3 of the 13 chapters are about the Nobel
Yeah.
Prize
Yeah.
specifically.
No, it's a
Yeah.
it's a bunch of little cutout pieces. You can actually see. I don't know if people can
Yeah.
see the
Yeah.
the sections there. You can see sort of
Yeah, they're in
three little
gray.
gray parts.
That's
Um,
right. Yep.
uh,
Choose your own adventure is
yeah,
the
here, let me
theme I
just do
wanted
this here.
to.
So yeah, so people can see them. So so I would love to talk about the future because I did an episode on this a couple of years back, and what I found really interesting was that is definitely the book is not closed on the search for primordial gravitational waves. That
Correct.
it's a frequency issue, and that there's a new collaboration that came together to continue the search. It's still a really fascinating question. So, can you talk about the sort of the state of the search as it stands now?
Yeah, it's really grown, despite, if you look at experiments, like there was an experiment called Opera, which was a search for faster than light neutrinos, claimed to have discovered faster than light neutrinos, shooting a neutrino beam between CERN and other detected at CERN. And launched a couple hundred kilometers away. And they claim these neutrinos were arriving 10 nanoseconds too early, caused a great amount of fanfare. They were later shown to literally, not leave the lens cap on, but they didn't connect a GPS timing fiber optic cable. And you look back, and now they corrected that. People resigned and so on. But there's nobody like going back and let's build Opera 2. Let's do the exact same thing again, because the science that we're looking for, I think, is still out there to be picked, and it's not at all clear that anyone will ever make the detection that we really are all seeking, which is to discover what happened in the first trillionth of a trillionth of a trillionth of a second after the Big Bang. But now we'll never make the same mistake again. Don't be fooled again. And in this case, we now know, thanks to BICEP, what needs to be done in order to build an experiment which will be, essentially immune to the same sorts of effects that we had. We still have the potential for confirmation bias, but hopefully, by building in safeguards like the ones I propose in the book, you'll be able to really make the discovery using bigger instruments with more detectors, certainly colder instruments and in different locations, and to require that multiple instruments see the same thing and agree with agreement. And that means competing teams The South Pole team, which I'm no longer affiliated with on a day-to-day level. I mean, we're still, collegial to each other. But, I joke the other title could be in the book, since I'm not working with BICEP, I was going to call it A Farewell to Arms, but that title was taken. So I guess
Yeah.
this guy Hemingway has that book. But
Bicep,
I
I
don't,
get it. Yeah.
I don't know what kind of a, career this guy Hemingway is going to have. So
Yeah.
maybe it's still good. But they're upgrading their experiment. They went currently to an experiment called BICEP 3, very creatively, and the next experiment, which is an array of telescopes like BICEP, is called BICEP Array. We, on my collaboration that I'm currently the leader of, called the Simons Observatory, is also building a series of refracting telescopes cooled down to a whisker above absolute zero. And these telescopes will be located in the high desert of northern Chile called the Atacama at about 5,200 meters, 17,500 feet or so above sea level. Just a complete otherworldly location. Think about the Sidonian plains of Mars or something like that. This is just like nothing like else on Earth. And we're building a huge set of infrastructure telescopes, a 6-meter diameter telescope, 20, 30 times bigger than BICEP. And we're also building these 3 refracting telescopes, very much cut from the same cloth and the same DNA as BICEP 2. And so the lasting, enduring lesson of BICEP 2 is these are incredibly hard measurements to do. The reason that people are so interested in them is that they could reveal the earliest signals that ever existed in our universe. They could reveal the presence of alternate universes. Multiverse is concomitant with most models of inflation posit that there are additional universes to the universe that we inhabit. Or in some sense, even more excitingly to other people, are the implications if inflation is not discovered. So what if we build these ultra experiments that are at the limit, the so-called cosmic variance limit, the limit beyond which we can't really improve upon, if such a thing is theoretically possible even, but let's assume that it is, and let's say we don't discover gravitational waves. Would that mean that inflation didn't take place? Or what if we see something different? What if we see evidence for what's called a cyclic cosmology, a bouncing cosmology? And there are many eminent theorists, from Sir Roger Penrose, who's a friend of mine, to Paul Steinhardt, who's another friend of mine, and Neil Turok. And they have a prediction that the universe in an inflationary scenario is very unnatural, and it's very baroque, and it has sorts of problems that they claim are every bit as fatal as the problems that the inflation model was designed to correct. Namely the flatness and or age and so forth of the universe. And of course, they're very much in the minority, as you say. First mover advantage conveys a lot of statistical power and drives the career choices for many young cosmologists. But one of the things that we could see, excitingly, would be evidence for a cyclic universe, which goes back millennia. Except we'd see it in a modern form. And in some sense, people consider that more natural, that the universe didn't come from nothing, and that in fact it came from something. And these two ideas are the inflation model and the cyclic model are the intellectual heirs of the steady state model and the Big Bang model. And who's to say right now which one is correct? But the debate will continue to rage on, and we hope to provide evidence that will give us data to kind of tip the needle in one way or another.
Yeah, I mean, at the end of the day, nature knows the answer, and it's just our job to listen to the point that we hear what the answer is.
That's right.
So, I mean, what would be a signal that you would see in your instrument that would tell you that maybe there's something to a cyclic universe?
Yeah, so the cyclic universe will present a very different type of signal. It would not feature B modes or gravitational wave, these twisting patterns of that are indicative of gravitational waves. They would not it would not produce them in the same way that inflation produces them. And so, in some sense, you're looking for an absence of something rather than the presence of something. So, we can falsify the bouncing models, which is what makes them interesting. In other words, science, in some definitions, I don't agree in all definitions. Karl Popper's presentation of it was that you could a true scientific theory, unlike say astrological theory, is disprovable in that
Right.
you can use data to prove it wrong. And inflation is very flexible in that there are many, there's no one model of inflation. There is one model of, say, nucleosynthesis. So we know how nucleons are synthesized together, and it's not necessarily like an interpretation issue. It's how do we actually make quantitative predictions from the theoretical inputs. You want to have minimum inputs, get maximum outputs. Inflation has maximum outputs in some sense. There's an infinite number of models, and so it's very flexible. It can accommodate a lot. The bouncing models can't, and they're sort of less flexible. So their virtue is that if you were to see gravitational waves, you could disprove that the bouncing model took place, the cyclic models took place. That, in some sense, is a virtue because it comports with the 500-year-old scientific method in a little bit more natural sense.
Yeah, but I mean, isn't there some hints of evidence of inflation?
There's a lot of evidence for inflation, but again, inflation is not, it's not the same as saying, there's a lot, isn't there some evidence for nucleosynthesis? I mean, we're at the tenths of percent precision on many parameters that describe the abundances of elements that trace their origin to the fiery Big Bang these first 3 minutes. But in inflation, inflation does not have to have taken place for us to see the universe as we see it today. In other words, it's consistent with it, but it also presents many other sorts of issues that people find challenging. The most prominent one amongst those being the multiverse, and that it's essentially inextricably intertwined with inflation. That if you have inflation, then you have a multiverse, and if you have a multiverse, you're going to change the name of your show, and that's
Yeah,
the least of it. I'm going to have your show.
multiverse
You're,
today. Yeah.
and you're going to be here with a book about dust. So everything can happen that's possible to happen. And so the kind of the initial conditions problem is pushed back a little bit, but you also have this complete burgeoning of potentialities for other universes to exist. And in those cases, then you start delving into anthropic arguments as to why we're here to be in a universe that's fit for us to be here to observe the universe, and you don't end up getting predictive power in such an ensemble of universes. It's sort of anything goes in a multiverse.
But you're more of an instrumentalist. I don't know
Yeah,
what the term is.
I play
You
the iPhone. Yes, I play an
yeah.
instrument.
But you build machines
Correct. Yes.
that that investigate certain portions of the universe. You almost hack the universe,
Yeah.
and that was something that I really loved about this. And
Yeah.
so it's like, are there, I mean, we see what's happening with, say, the Large Hadron Collider, that we have sort of, it did its one job perfectly
Yeah.
well, and now it hasn't been able to turn up any evidence of any of the supersymmetric particles, any of the dark matter particles, any of these
Correct.
heavier particles that are out there. And now people are starting to have this conversation about, should we just build something that is bigger, more brute
Right.
force?
Mm-hmm.
And it does feel like there's a real opportunity now to build some of these machines that, and I call a telescope a machine in this situation,
Sure.
to
Yeah.
explore some of these areas that are maybe haven't been investigated enough, to just see what turns up, to see what kinds of interesting discoveries. And so, with the Simons Observatory, do you see other kinds of just interesting, that surprising outcomes that maybe you
Yeah,
hadn't been planning for?
absolutely. So the patron of the Simons Observatory is Jim Simons, a world famous mathematician, 20th on the Forbes list of billionaires. And he's of the, he has a personal predilection for these bouncing cyclic models. In some sense, they appeal to be more natural to him, but he's not a cosmologist. So I was talking to him about it not too long ago, and he's saying, well, it seems like it would have an implication even for the existence of God. And now here's a guy, he's a secular guy and mathematician, first-rate scientist, has developed many things in his career, and he's talking about the implications for something so a metaphysical a conjecture. And I just think it's so interesting because I love my colleagues here at UCSD, and some of them down the hall will be trapping atoms and doing all sorts of other cool stuff. But those sorts of experiments are very important, but they are also they have a different level of kind of connection to the personal side of science. So I always feel like cosmology has this great story to tell, and unfortunately there aren't as many great storytellers. And most of the storytellers who are great are friends of mine, many of whom put their names on the books and endorsed my book. Brian Greene and Sir Roger Penrose and Martin Rees, and they are theoreticians. They're not in the trenches building the equipment, deploying it, and shooting them all around the world, and taking data for decades in some cases. And I felt like that was something that was a lacuna in the popular science book field, where people describe, well, what is it like to build a telescope? Why do you do these things? And are you just kind of like a plumber and electrician? Or do you have, you're just a technician? Just, I don't mean in a pejorative sense, but like, are you just a technician, kind of contributing in that sense? Or do you have a deep visceral connection as these brilliant theorists do. And I want to show that, yeah, we do. We're not just, kind of just putting on our hats and just and connecting pipes together. And as I said, nothing's wrong with that. But the bottom line is, for us to do what we do, we are the ones that are going to put the checks on the theories. And one of my friends said, he's a theorist, and he said, like 99% of what theorists do is wrong.
Yeah.
And we're comfortable being wrong. And, but when you have a big announcement, that's why, this thing that's coming in 2 days from the Event Horizon Telescope is so exciting, because, it has to be blessed by multiple levels of people, and their paper has to have been vetted and accepted. I would be very surprised if it wasn't accepted and ready to be published in a major journal. And so there's a lot on the line. Now, we didn't do that for BICEP, and that was probably to our peril, and we're going to correct that in the future.
Yeah.
But yes, it's sort of the greatest things that you can do, in my opinion, is that to be a good experimentalist, you have to be a good theorist. I mean, you don't have to create new theories. That's not my job. But you have to understand the theory at a visceral level so that you can talk to a theorist to understand what you're doing. And I find we do that. I teach my students that. I've got 9 PhD students. It's very important for me that they know the theory, and not as much goes in the opposite direction, unfortunately.
But it feels to me like I absolutely have a preference for experimentalists. Like it feel like, for me, that's where the rubber hits the road.
Mm-hmm.
That, like, obviously the work from the theorists is absolutely critical, and I think the some of the greatest examples of this are things like, people figuring out that they should be seeing the cosmic microwave background radiation, and then
That's right.
And then that leading to the actual discovery, the accidental discovery, by Penzias and Wilson. But and of course what happened with the Higgs. But I also love the work, say, in discovering dark matter by Perlmutter and team.
Or dark energy.
Dark energy, sorry, with Perlmutter and team. And just this thing that they were just trying to make precise calculations about something, precise observations about the distance to supernova, and discovered something that was surprising to them.
Yep.
And that I think that, and I think there's a pretty, again, I'm not a physicist, I'm just a journalist, but my job is to report on every gruesome detail of all the stuff that happens. And I definitely see, things like what happens with string theory and some of these other theories, that people sort of get lost in the weeds for a long time. And yet it feels to me like a lot of I'm always really excited when the new experiments are figured out and developed and implemented. And then I also feel sad when an experiment gobbles up too much budget and isn't able to, that smaller, more interesting, more out there techniques are proposed. And that's why, reading sort of the development of the simplicity of the BICEP and the BICEP 2 experiment just really felt like perfect, there's one job, it's going to figure this out really well and go from there. Neil Yu is asking if you could hook us up with Neil Turok at some point to interview. So
absolutely. He's out of a job now. He was the director of Perimeter.
Yeah.
And now he's not out of a job, but he's no longer the director. So yes, he's
yeah.
a friend, and just shoot me an email. I'll be happy.
Yeah, I'll reach out to interview some of these people.
And Paul Steinhardt, you should interview too. He has a new book about discovering quasicrystals, a feat which he won't admit it, but I will say, basically won a Nobel Prize. Actually, it was something like 37 years ago today. The Nobel Prize winning discovery for quasicrystals was made by Shankman and et al. And but Paul was really instrumental in predicting it, and some say he lost out on a Nobel Prize opportunity for himself.
So what are some, if you had more money to spend on some instruments, some perfect machines, what are some observational instruments that you would love to see built?
Well, I mean, I'm of course biased towards what I do.
Yes, of course.
I think
the project you're working on, the Simons Observatory, is the greatest thing, and there's nothing you'd rather be.
And
there
isn't a success. There is a successor potentially to the Simons Observatory, which would be sort of $1 billion class experiment. We're only $100 million project, but poor pitiful us. But the successor, sort of $1 billion class experiment, called the Department of Energy CMB Stage 4 experiment, which is being led by many of my friends and colleagues in the field. I'm not particularly involved in it yet, but this instrument would be, many, many times more. It would be essentially multiple copies of the Simons Observatory, but in addition to being in Chile, would also be at the South Pole, Antarctica. Now, that experiment would potentially reach. There is a golden, goose that stops laying eggs eventually. So there is a limit, even if inflation didn't take place. There's a limit beyond which you cannot probe anymore using gravitational waves in this B mode pattern that I described. And that limit, it turns out, it's many orders of magnitude lower than what we're going to be able to do with either the Simons Observatory or this $1 billion experiment. But my dream would be to do that, because if you could
Right.
build that experiment, and then you would rule out that inflation took place down to the minimum possible level beyond which the bedrock prevents you from drilling deeper into the signal. So beyond that level, if you didn't see something, uh, then you would have to say, well, either inflation didn't happen, and therefore an alternative model, potentially a cyclic universal model, must be true. And that would have dramatic ramifications for science, for theology. I mean, what if the Bible's wrong? I mean, it's not exactly a science book,
Well, I mean,
right?
a
So
cyclic universe, doesn't that just push the, like, what started the whole cycle in the first place? Doesn't it just push the question back in one level?
well, it's sort of interesting because this cyclic universe, in some sense, is more palatable, because at least it posits that there's an unending cycle of universes, unlike a true steady state universe, which is the same forever, which we now know is impossible. So it does push it back, but at least it significantly avoids the question of where, how does something come from nothing, right? That even the laws of physics did not exist prior to which. It also provides an answer. My favorite question, that I'd like to answer, is what happened 15 minutes before the Big Bang, or
Yeah.
the Tuesday before the
Yeah.
Big
The
Bang, what
last
happened?
15 minutes of the previous universe.
Yeah, it could
Right.
be, right? And
But
now
that's
it's not.
still, I mean, come on, it still pushes the question back. Like, you still have to say what started the cycle going.
Well, you could say the cycle is truly infinite, right? You could say it has been going on forever, and it's just this phoenix repeating over and over again from the ashes of the previous universe. But there's one other aspect of this ultra future. If I have Cain money,
Yeah.
if I
Yeah.
have your
Yeah. The
money, and
Cain.
then
Yeah. After. Yeah.
unlimited
Exactly. We'll put.
funds, yeah,
Yeah. The
the
Cain fund.
Cain Observatory, what it would do is, if it did detect these waves of gravity, and it didn't detect any sort of signal whatsoever, then it would mean that general relativity is wrong. Also, in a precise sense, I just wrote a paper with some colleagues in Israel that describes, kind of the ultimate experiment, the ultimate limit is provided by what are called the secondary fluctuations, these scalar perturbations in the early universe's curvature, energy density, etc. They must produce a manifestation of gravitational waves, meaning that if general relativity is correct, meaning if you didn't see them, then that would imply that the universe did not obey general relativity at its earliest moments. Now that's heresy, right? I mean, you're basically saying that's heresy. And the other thing that we could do, and we're just starting to do this now with the CMB and other instruments, is that we're looking for what's called a violation of Lorentz invariance. So we think the universe is sort of mirror symmetric, it's charge symmetric, it's time symmetric, if you put all three of those together. But we know the universe doesn't respect what's called charge and parity. So if you invert the charge of all nuclei, and you invert their helicity, or their direction of spin, you can get different physics. In other words, if you drop a baseball in a mirror, you see the same physics. If you run time backwards, and the baseball will go up, because the laws of physics are symmetric with respect to change in time. But if you change charge and time, or charge and parity rather, in mirror symmetry, you get these strange effects. And by looking at the most distant light in the universe, namely the CMB, we can test if this symmetry is truly a fundamental symmetry of nature, or we just think it is because we've only tested it in the laboratory or the solar system. So we have not yet tested beyond the solar system, and now we're using the entire universe as our laboratory. And with the Cain Observatory, we hope to do
Right. Of course. I look forward to funding this these observations.
May you be so wealthy, sir.
Yeah, exactly. But I think, like, I think, you talk about a bit about, like, having a chip on your shoulder. I think anybody who wants to do things has a chip on your shoulder, and the question is, like, is it a good chip or is it a bad chip? And do you use the energy for good or evil? And I think that if you use that, I am absolutely driven to compete, but I'm also more driven to help other people succeed. And I think that as long as that's the thing that's more compelling to me, then I think so. So I think as you go down this pathway, my only advice is you just be careful with your biases as you discovered the first time
Yeah,
around, right?
absolutely. I mean, really confronting that, and, and looking into, other sources of ancient wisdom, and you look at things and you see that this is just not unique. Scientists are people. And I think that's a huge misconception, that we aren't driven by these things. We're driven by them. And look, on a daily basis, am I speculating about whether or not the universe was cyclic, or whether or not there's a God that kicked off the universe? No, I'm thinking about, why doesn't that damn resistor get to 17,000 feet in time to meet the compressor? I'm thinking about systems, and I'm really more in a kind of project managerial mode more than ever. But and in that sense, you do have to be a small business person, an entrepreneur. You have to interact with people, and so yeah, don't be a jerk, don't be evil. But what we're trying to do is so fundamentally astounding and intriguing. As I said, I don't think we need more stories to tell in cosmology. We have them, but we need storytellers. And to me, that comes with humility, as I say in the book. I think it was a humbling experience, but it wasn't a humiliating experience. I don't regret it, and I think it clarified through new vision that I have now, as you say, this notion of what should science really be about. And it used to be, just to be completely honest with you, when someone make a big discovery, you're like, oh man, does that, like, is the Nobel Prize a pie? Is there going to be one less piece of pie left for me? And now I'm totally honest. People can, they're free to leave a 1-star review if they like. It would be my first, so I know who you are. But the
It happened
but
today. Yeah.
yeah, exactly. That's right, from Vancouver. No, but looking back and thinking about what happened, I really don't wish that. It's almost like you don't wish the Nobel Prize on anybody,
Yeah.
because it's such a burden. I mean, I had a Nobel laureate in this office talking with me, and he read the book, and he read the interview, reviews of the book, and he's got his own quips with the Nobel Prize too. And a lot of it, one of my late colleagues here, Roger Tsien, who won it for an invention of microscopy and chemistry, he said like the last peaceful day he ever had was the day before he won the Nobel Prize.
Yeah.
So I think, be careful what you wish for. And now I've learned that early enough in my life, my career. Now I can, really feel and mean it. And I think people say, oh, you're a hypocrite, you don't mean it. And I say, well, look, you can test my sincerity. Just, get them to award me the Nobel Prize. If I don't reject it, I'm a freaking hypocrite.
Yeah. I I think you'll accept it.
I don't know.
Yeah.
I'd have
I'll
to
take
see if
one.
it's convenient.
Yeah,
That's right.
exactly.
Yeah.
I
No
would take one.
physicist has ever no. There have been rejections in almost every field. Medicine,
Yep.
even, and then peace, certainly economics. Maybe, but no one's ever rejected the physics prize.
Hawking
Is
rejected lordship
did he?
from
Did he
from the
really? Okay.
Queen. Yeah, he
Mhm.
rejected being called Sir Stephen Hawking, which
Oh,
is why he never
okay.
was. So,
Interesting.
of course, as a Canadian, that's still an
That's right.
option for me. Well, Brian, it was a pleasure to talk to you. Of course, I'll hold up the book again. People
Yes.
can read sort of the see the blow by blow of how you went through what you went through, both the discovery and how it all unfolded in the end. And sort of, and if people want to follow along on what you're working on now, where should they go?
Well, I'm pretty active on Twitter, mostly at Dr. Brian Keating. I don't really do Instagram or whatever, but I do have a website and I have a mailing list. And what I want to do for your first 10 respondents, listeners, whatever, that sign up for my mailing list, U.S. addresses only, I'm afraid. Actually, I could probably do it for Canadians too. I will send a piece of space dust, which I think I sent to you, a chunk of space dust. You might have
Yeah.
misplaced it, or it got sucked up in your vacuum cleaner, maybe.
Well, there was like a bookmark that came with
Well,
the,
there's
and
a
then the,
bookmark, but there's also a little rock, right? There's a
yep,
meteorite that came with it.
yeah.
So I will send a tiny meteorite to your first 10 listeners that sign up for my mailing list and use hashtag universe today. So
Oh,
I will mail it to you guys,
oh, that's
US or
great.
Canada only.
So what's your website? I'll put it up on the screen so people can see it.
It's briankeating.com.
Okay. And show people how to do this.
Yeah.
Let's see.
Yep. Use
Yep,
hashtag
there we go.
universe today and send me a note and sign up.
Yeah, and so if you go to briankeating.com, the very first thing that happens is it pops open his mailing list, which you can join.
Yes.
Perfect. Awesome. Well,
Great,
Brian,
Fraser.
absolute pleasure to chat with you, and good luck with the work that you're doing with the Simon's Telescope. I really look forward to that next announcement the one that has the primordial gravitational waves for
All
real,
right,
for real.
you'll be the second to know.
Perfect. All right. Thanks a lot. And thanks everyone for
Thanks, Fraser.
watching. Thanks for the moderators. Apologize for me hogging all of the bandwidth tonight, but sometimes that's just how we roll. I had a million questions I want to talk to Brian about. So don't worry.
Yes.
Next week I think we have Chad, our producer. I think is the plan next week, and then after that is going to be Jeff Notkin, the new president of the National Space Society. So that'll be a fun conversation. All right, so thanks, Brian. Thanks everyone for watching, and
Thanks,
we'll see
Fraser.
you all next week.
Take care.